Hello there.
Can you hear the sound? We're the revolution. We're the revolution. With the ground beneath your feet, with a whisper in the trees. Do you feel us watching? Hunger in our eyes, victories on our minds. It's our time to rise. Can you hear the sound? Can't stop us now. We're not backing down on what we're doing. Things are about to change, it's evolution. Voices shake the ground, you feel it moving. We're the revolution. Can you hear the sound? We're the revolution. We're not backing down on what we're doing. Things are about to change, it's evolution. Voices shake the ground, you feel it moving. We're the revolution.
Good evening, welcome everybody. This is Obi-Wan Tez for Simplex Pachinko. We are going to be doing some math tonight. Bit late of a stream, but I was watching somebody play Expedition 33 for a bit, so you know. It happens. Right. So for tonight, we have a bit of the logarithmic differentiation that we were looking at last time. Right, I think we found the derivative of x raised to the root x. Yes, yeah, we did. So then, the next section was talking about L'Hopital's rule. Which, just as a reminder, was... Okay, good times. And we could turn that back down, I suppose, just a little bit, but... Okay. L'Hopital's rule states that if we're trying to take the limit as x goes to some particular value c, it doesn't really matter what it is, whether that be infinity, 0, or any other finite number, and we have a function that looks like f of x over g of x, then that's going to be equivalent to the limit as x goes to the same c value of f prime of x over g prime of x. Now it's really important that everybody understand that this does not mean, right? This does not mean that f of x over g of x is equal to f prime of x over g prime of x. Right, and also nor is it equivalent to the derivative of f of x over g of x. Right, none of these statements are generally true. These just happen to work out. These happen to work out at any particular point that you want to look at. So any individual point, this will be true. It's Zach, everybody. Woo! Good evening, Zach. How is little today? I mean, just started, so yeah, it's going pretty well, I think. You know, we probably did some of these, if not all of them, last time, but like, it's fine. It's been like a month since I've done cracking the GRE, so we'll just do the whole thing over again. It's all good. For anybody who didn't know, and I didn't actually introduce it at the beginning, professional. We're working out of Cracking the GRE Math Subject Test, second edition Princeton Review from 2002. Hasn't changed all that much, but nonetheless, this is for the graduate record exam most of the time. A lot of school, well, okay, way back when, in days of yore, schools would ask you to take the GRE, Graduate Record Exam, in, I believe, English, just so that they would understand like how well you could write and read, and then also in like a basic math or something like that, like a general knowledge. And then there was the subject-specific tests. So this is the math subject test, yes. Maybe there wasn't a general knowledge one. I don't remember. Or it was like or it was very fast or something. I don't know. It's been 20 plus years, so it is. Okay. Yeah, it was not like quals. Okay, so we have here the request is to evaluate the following limits. So we have the limit as x goes to 0 of sine of 4x over x. Which will be equivalent to taking the limit as x goes to 0 of the derivative of each of those. So again, here this is d dx of sine of 4x divided by derivative of, wow, derivative of x with respect to x. So here this is going to be the limit as x goes to 0 of, at the top we have the derivative of the sine function is the cosine function of 4x, and then using the chain rule, take the derivative of the inside, and that's going to be 4. And then we take the derivative of the denominator. Derivative of x with respect to x is 1. So there we go. We now have taking the limit as x goes to 0 of the cosine of 4x times 4, or 4 cosine of 4x. Here the cosine of 4x evaluated as x goes to 0 is going to be 1. And then the numerator is just going to be 4, or 4 times 1. Right? Easy. Okay, so then they give us one that's ever so slightly harder. This is going to be the limit as x goes to 1 of square root of x minus 1 over the square root, the cube root of x minus 1. Sorry, both of those should have been the root of x minus 1. Right, so there is actually a slightly easier way to maybe work with this one, which would be to try and get terms which are going to rationalize the denominator or unrationalize the numerator in order to be able to plug in the value of x equals 1. So in this case, I don't actually think it's that much easier. But either way, yeah, we can either rationalize or unrationalize depending on how it's going to work. But in this case, yeah, having a cube root makes it slightly more awkward. It's fine. However, in this particular case, we can use L'Hopital's rule to bypass all of those concerns. And for this, we say we want the limit as x goes to 1 of, take again, the derivative of the numerator. I'll stop doing this on the next one, I think, but nonetheless. of the cube root of x minus 1, which is going to make for us the limit as x goes to 1 of the derivative of the square root of x is going to be 1/2 x to the negative 1/2 divided by okay. Sorry, just checking to make sure this was actually going random and not just in order. The cube root of x is x to the 1/3. So this is the same as making x, nope, sorry, 1/3 times x to the, here this is going to be 1/3 as an exponent minus 1. It's just the power rule. So negative 2/3 as an exponent. Right, and in this case, if we plug in 1 to each of these, x becomes 1. Raised to any power is still going to get us 1. So this is very nice. This one's just going to get us 1/2 times 1 over 1/3 times 1. And here, if we multiply both top and bottom by 6, we'll get the appropriate values. So 3 on top and 2 on the bottom. Okay. Let's see, the limit as x goes to 0 of x squared over, I probably should have done something first, which is to remind ourselves that the first thing you need to do is check to make sure that this is, in fact, in an indeterminate form. So here, right, you can't actually just take the derivatives of both top and bottom without concern, right? This is if and probably only if is of an indeterminate type. Then do that. So, have to make sure it's indeterminate first. And that was my mistake. I should have done that for all of these other ones. So, real quick, right? If we plug 0 into this directly, we get 0 divided by 0. Easy enough, right? When we get 0 over 0, we don't know whether this is going to be an infinite value, a finite value, or 0 itself, which I understand 0 is finite too, but it's of a different class than just a finite number. Alright, so this is indeterminate. So therefore, we can go there. Right, second one, same deal. So here, if we plug in 1 directly, we end up with square root of 1 is 1 minus 1 divided by cube root of 1 is 1 minus 1, which is 0 over 0, which is indeterminate. Right, so here, again, same deal. We want, is this indeterminate? Plug in 0 for the top. We get 0 squared is 0, divided by 1 minus cosine of 0 is 1, which is 0 over 0, which is indeterminate. not in debt. But Obi, just factor the denominator. I mean, you're not wrong. You can factor the denominator anytime you want, and then work with making it either rational or irrational, depending on what you have. Again, if you went with the cube root one here, you can, in fact, factor the denominator and then see, A, if anything cancels out, which in this case, not so much, or A. B, if you can either rationalize or unrationalize by multiplying both top and bottom by something, wink, wink, nudge, nudge, that is going to eliminate the problem in the denominator, and then do what, we don't even care what happens to the numerator. And in fact, because we're looking for a determinate form, we can go the other way too. So if we can multiply top and bottom by something that rationalizes the numerator, then we can say, well, I don't care what happens to the denominator as long as it's determinate. Let's just do that. Could divide by the square root of x. Let's try. Because why not, right? We've got nothing but time here. This is a good classroom. Right, so can we do limit as x goes to 1 of divide by or multiply by 1 over root x over 1 over root x? Right, is equal to limit as x goes to 1 of, this is going to be 1 minus 1 over root x over, I mean, that's going to get you a 0, right? And then this is going to be, x to the, let's see, that's going to be a negative 1/2 and a positive 1/3, so that's negative 1/6. Minus 1 over root x. Yeah, it's still 1 minus 1. So you're still going to get an indeterminate form for this. Okay. So we take this one, and again, this is L'Hopital's rule, so take the derivative both top and bottom. This is going to be 2x divided by a negative cosine of x. We take the derivative that is a positive sine of x. And when we plug 0 into both of these, this is going to be 2 times 0, which is 0, divided by sine of 0 is 0, right? 0 over 0, which is still indeterminate. So now what? Right, rather than getting into an infinite loop, let's just say, well, these are our original functions now. So the derivative of 2x is going to be just 2. The derivative of sine of x is going to be cosine of x. Plug in 0 to those, and now we get 2 divided by 1, which is just 2. Which then goes back up 2 layers, and we say that, well, the original limit as x approaches 0 of x squared over 1 minus cosine x is just 2. And here's the thing, right? You could always just check it. Flashbang out. You could always just check this. So we had x squared over... Nope. Oh. Oi. Over 1 minus cosine of x. Right, so it's blindingly obvious that this is getting really, really close to 2, even if the number itself is not exactly 2. We know here, right, 0, undefined. Right, that was expected. But if we get really, really close to it, we're so close to 2, like, come on, obviously, right? It has to be 2. In theory, It could be like 2.0000001 or something like that. So you do have to be careful, and we do want to get an actual numerical value for this. See, I told you. That's a lie, but okay. Yeah, see, the problem is that when you get really, really close, our numerical approximations do all sorts of weird stuff. The error in this is so wild that it's just causing all sorts of problems. It's using approximations to calculate stuff, which is causing all sorts of issues. So, we're getting all these values. This is all a lie, right? But this is the point, is that like when you start getting really, really close to 0 this way, it's doing some wild stuff in this approximation calculation. So like, let's do it mathematically to make sure that this actually is a value of 2 and not that. How you doing, caller? Woo. So we find here that, yeah, we did this whole L'Hopital's rule thing, and now we get a value of just 2. And now we don't have to worry about these, like, tiny errors throwing off the whole calculation. All right. Right, so limit as x goes to infinity of 1 over x times the quantity pi over 2 minus arctan x. Again, here, x going to infinity is going to cause us some potential problems because what we have is a 1 over infinity times pi over 2 minus pi over 2, because here the arctangent of x as we go off to infinity gets us pi over 2. So if you remember, the graph has two asymptotes, one at pi over 2 and one at negative pi over 2. Y equals those. So those horizontal asymptotes, as we go out further and further, are going to get our values for those. Time to do Arnold's limit. I'm right here, kill me! That one. I'd say he reached his limit. Right, so this is 1 over infinity times 0. Infinity times 0 is, by itself, indeterminate. Troll limit to compute. Keep kicking it around, it's fine. So here we want to do the same thing. The thing is, we don't want the numerator to have the function y equals 1, and the denominator to have the function x times pi over 2 minus arctan x. That would be insane. Don't do that to yourself. You get a 0 on top, and something really ugly on the bottom, which probably has the same indeterminate form. So instead, we say let the top be 1 over x, and then the bottom be pi over 2 minus arctan x. Sine of tan of x minus tan of sine of x over arc sine of arctan of x minus arctan of arcsine of x. Whoa. You have to apply it 6 or 7 times. No, thank you. Okay, so when we do this, we're going to take the derivative of the top, right? So we can do ddx of the numerator, and ddx of the denominator. And then we're going to take the limit as x goes to infinity of derivative of the numerator is now going to be, right, this is x to the negative first. So negative x to the negative second over pi over 2 is just eliminated, minus 1 over, this is 1 minus x squared. You posted a video on Zach's server. All right. You predicted 2025? I don't think I understand that one. Okay, so we divide out the negatives. That's the easy part. Oh. God. Boo. Alright, and then multiply both top and bottom by x squared times 1 minus x squared. And that's going to get both of those to Alright, that's going to cause both of those things to come down to this, and either we could do the pre-calculus thing of being like, hey look, these functions are of the same order, right? They're polynomials of the same degree, so we could just use the ratio of their Lie coefficients, or we could do L'Hopital's rule twice more, because you're going to have to do it twice if you do L'Hopital's rule here, or, because this is, again, negative infinity over infinity is itself another indeterminate form, or use the, like, unit 1 calculus method of saying, okay, well, we could just take the limit as x goes to infinity of, use the denominator and divide each part. So this is 1 over x squared minus 1. That's much nicer. So here, the limit as x goes to infinity is going to be 1 over infinity is 0. 0 minus 1 is just negative 1. Right, and then, of course, again, we could go back to the original function and say that we want what is 1 over x times pi over 2 minus arctan of x. And then zoom out. I should have just hit home, honestly. Right, as x goes to infinity. Huh. Hang on. I forgot something. The negative. No. No, that was here. That divided out. Yes. Oh. No, I forgot something really big, and that is the arctangent is not, the derivative of the arctangent is not 1 over 1 minus x squared, it's 1 over 1 plus x squared. Boo. I said it so confidently, everybody just believed me. Catch me on these. Yeah, much better. It's 1. This is why we do graphs after we solve them. Right, so here we have a value of 1 that we're approaching as we go out toward infinity. And as always, we could just say, okay, take the x-axis out to like 1,000,000 or 100,000. Right, and it's close enough to 1 that it's not even registering that it's anything different. So... one over infinity is not... The limit of 1 over infinity is 0. Fine. Hang on. There you go. It even says so right there in the book. See? Yeah, no, it's the limit of x going to infinity of 1 over x squared. That is 0. And don't you forget it. Well, Dr. Zach, what would you say? The limit as x goes to 1 from the positive direction of x raised to the 1 over x squared minus 1. Again, here, we want to just double check, make sure everything works out the way we think. So plug in 1. Again, it's not 1, but we're plugging in 1 to see what would happen. So this is going to be 1 raised to the 1 over 0, right? 1 minus 1 gets us 0. Which is going to be equivalent to, in the limit, 1 raised to the infinity, but it's not 1, right? It's off by a little bit. But the question is, because this is indeterminate, right, will the infinitesimal base 1 plus, you know, some delta x, essentially. Go to 1 faster than the exponent goes to infinity. Right? We don't know. That's the point. And you can do a functional analysis to determine, well, which one is accelerating faster. Oh, look at that. We have to find the rate of change. That's what we're doing, right? We're trying to figure out, is the base going to go to 0? Sorry, is the base going to go to 1 faster, in which case, essentially 1 raised to a very, very large number is going to be really, really close to 1, or it's eventually going to be 1, or is the rational nature of the exponent, 1 over 0, going to get us something that goes off to infinity faster, in which case we've got like 1.00000000001 raised to whatever that makes the exponent. Is that going to start accelerating off toward infinity faster? So that's our basic question. So then we come over here and we say, all right, based on that question, right, we come over here and we say, all right, we're going to take the derivative of the numerator and denominator. We don't really have a numerator and denominator here, so we have to make one. Well, one of the ways that we do this is we could say the limit is going to be this thing, which means that the natural log of the limit is going to be, natural log of the limit is going to be the, limit, x goes to 1 from the positive direction, of the natural log of x raised to the 1 over x squared minus 1. So this is going to end up getting us the limit as x goes to 1 from the positive direction of, here the exponent comes down front, and now we've got the natural log of x multiplied by, separately, 1 over x squared minus 1, which then makes the limit as x goes to 1 from the positive direction of natural log of x over x squared minus 1. Oh, look at that. Now it's workable. Now, we can also do a functional analysis on this and say that the natural log is going to accelerate a lot slower. If we just kind of look at the pre-calculus version, the numerator is going to accelerate toward infinity, but it's not going to infinity. Okay. If it were going to infinity, this would be a lot easier. Which one's going to 0 faster, right? But natural logs, generally speaking, go pretty slowly, and quadratics typically go pretty quickly. But the problem is that now we're going to somewhere in the middle of the curve, not something way on the end. If it were infinity, this would be blitheringly obvious that the numerator would accelerate a lot slower. And the denominator would be going faster. So in this case, this would be going to 0 if we had an infinity here. But we don't. So let's go back. Since this is going to 1, and only from the positive direction, and realistically, in this case, it doesn't actually matter which side it's coming from. I might regret that. Hang on. Okay, we'll figure it out. Okay, take the derivative of each part. The numerator, the derivative of the natural log is 1 over x. Yeah, one's positive, one's negative, so it may very well. And then the denominator, this is going to be 2x. And here, we can multiply both top and bottom by x. And we end up getting the limit as x goes to 1 from the positive direction of numerator is going to be 1, denominator is now going to be 2x squared. And we go to x equals 1. Again, from the positive direction, it's equivalent to just saying at 1, or even from the negative direction, in this case. This would end up getting us a positive 1 over 2, 1/2. However, if we ended up coming at it from the negative direction, we'd have to be careful. Because these two things don't have the same limit. So you have to be careful about what's going on and when. So if we go to, actually we're not done with this, but give me a sec. If we go to the natural log of x part, what was it, x squared minus 1. Right, at the value 1. Okay, we're actually okay here. We get 0.5 from either direction. So this would be okay from either direction here. Yeah, so this gets us a positive 1/2 from either direction. But again, we just have to be careful and make sure that that's not going to mess anything up. Okay, yeah. So the natural log and its derivative, when put in ratio with x squared minus 1 and then 2x, respectively, are going to have the same ratio. The problem is that I'm not thinking in terms of ratio, so it's fine. Right, ratio is what matters. So then we do like 1 over x over 2x, like that, right? So both of these have the same ratio at this location. And you can immediately see, right, L'Hopital's rule does not work everywhere. It's just at this point where the original function is indeterminate and the all of its derivatives can be indeterminate, or you stop when you find one that isn't, one that is determinate. And once you have that list, then you can focus on this one point, right? All of the indeterminate values, all of the indeterminate ratios have the exact same limit value. So again, you have to be careful with how this works. The second you say, oh, I'm going to pick something that doesn't, that is determinate, then you have a problem. Okay, so this, again, this is not L. This is not what we were trying to find at the beginning. This is the natural log of L. So what do? right? Make it the exponent on e. So this is going to be e to the natural log of L is just L, is equal to e to the 1/2. So, looking at this, we're now going to plug in the third, which was the original, right? So x raised to the 1 over x squared minus 1. Uh-oh. Oh. Yes, this is fine, because this number here is not 1/2. It is e raised to the 1/2. Jeez. Just out of curiosity, if we made this f of x, and we made this g of x. Okay, now we have to be careful about how we say this. Let's not. let's do like m and n. Because these are not f and g. Okay, what if we did e raised to the m of x? Oh, would you look at that? E raised to the n of x. See, there you go. So these now have all the same value at 1. This value, 1.648721. Right? 1.6487. Yep. Right in between 1.649216 and 1.648392. So not, again, not literally the average of them, but close enough. And again, here we have, what's the other one? 1.648969, which is not the same as the other one, but it's really close. And 1.648556. Again, not the same as m of x, or e to the m of x, but really close. And if we zoom in far enough, we should be able to see the difference between them. In theory. Oh dear. Huh. Okay, maybe not. I thought we had actual differences, though. I mean, that's within error, so it's not going to show anything useful. Anyway. So yeah, e to the 1/2 is going to be our limit for that one. Or square root of e, yeah. Okay. And what about a sequence limit? So this was saying, what's the limit of the sequence? A sub n of natural log of n bracket squared, all divided by square root of n. So with this, we could say that try the continuous function. A of x, which is equal to natural log of x bracket squared all over square root of x. So if we do the continuous function, it should have all the same values, because here what we're doing is we're saying that, okay, n is just going to be the positive integers, maybe can include 0, but Yeah. Sometimes people include 0 in their n values. This one's not going to because the denominator's going to make it undefined. So we want... Or I guess we could go the other way around, right? But whenever x is the same as a positive integer n, then we're going to get the same function values. So capital A of all x, capital A of all n is going to be equal to lowercase a sub n. Right, for all n being positive integers. So in here, what we are looking for is what's the limit as x goes to infinity of capital A of x. And then that's going to get us an equivalent value for the sequence limit n going to infinity. Just the only problem is that limits really only work, if you think about the concept, limits really only work when you're talking about continuous functions, because you're trying to get ever and ever and ever closer, and with sequences our delta value, like the difference that you can go, the smallest possible difference that you can move is 1, which is huge, right? Especially when you're talking about the smallest delta that you could possibly think of on capital A of x, the continuous function, is an infinitesimal, right? It's infinitesimally small. So 1 is infinitely larger. Right, so the limit as a goes to infinity of capital A of x, we're going to do the same check to make sure that this is in fact indeterminate. Right, this is going to make limit of x going to infinity of natural log of x bracket squared all over square root of x is going to get us, the denominator is going to be an infinite value. The numerator is going to be the natural log of infinity is also infinity, and then squared is also infinity. So yeah, this is indeterminate. Alright, that's not a polynomial, so we can't use the pre-calculus cheat there. I say cheat. Okay, so we know that the limit of x going to infinity is going to be equivalent to the derivative of both the numerator and denominator individually. Denominator is nice and easy. Okay. So this is the limit as x goes to infinity of, this is going to be 2 natural log of x times 1 over x, which is the derivative of the natural log of x. So here we have to use the chain rule to make sure we get all of the parts. Take the derivative of the denominator, which is x to the 1/2, is going to be 1/2 x to the negative 1/2. We can multiply both top and bottom by x, which is going to get rid of the 1 over x on the top. It's going to be equivalent to x going to infinity of 2 natural log of x divided by, and this is going to be a 1/2. You know what, let's make it 2 on the numerator and denominator as well. So that's going to get us a 4 in the numerator and a regular 1 in the denominator. X times x to the negative 1/2 is going to be x to the 1/2. So now we've got 4 natural log of x over the square root of x. And again, we have to look at what happens when we plug in infinity. This is going to be infinity divided by infinity. So again, indeterminate. So again, do the derivative. So we take the limit as x goes to infinity of 4 times 1 over x, nope, not a half, 1 over x over, again, 1/2 x to the negative 1/2. Again, multiply by x over x, and again, let's make it 2x over 2x. Just going to make the limit as x goes to infinity of 8, and 1 over x times x is just going to be 1, so that's gone. And in the denominator, 2 times 1/2 is 1, and then x times x to the negative 1/2, we already played this game. This is x to the positive 1/2 again. So then this is going to be 8 over infinity, which is going to be going to 0. Right, in the limit, we're going to get 0. So we could look at this again from the perspective of ln x over, hang on, what was it? Natural log of x parentheses squared over square root. Right, going to 0 could also be fun, but that's obviously going to positive infinity. And actually, I don't think that that's indeterminate. Right, as we go to 0, natural log of x goes to negative infinity, but squared it goes to positive infinity. And then the denominator, as we go to 0, is going to cause the overall fraction to also go to infinity. So that's just going to infinity. That is determinate. So going to x going to 0, we don't need to do L'Hopital's rule, and in fact cannot do L'Hopital's rule. Going to 1 is determinate because we have a 0 over 1 from the initial fraction. And going off to infinity is the only one that's the odd one out. So, cool. We're going to take an ad break here. We've got 1 minute till they start. I might as well just activate it. Go grab a drink, cycle that water, stand up, stretch, do all that fight, whatever it is that you're doing. And see you all in 3 minutes. Thanks so much for coming. Righto. So, we are going to, as per usual, do some Tai Chi. I just went today. Got a good re-up, so haven't seen my instructor for like the last month. So today was good. Did some good work on the form. Reminder of how things actually are supposed to look and work. Reminder of where to, put your force, what to do with it, all that good stuff. So we did a number of exercises working toward firming that stuff up, and then we just kind of played around for a while, where basically he was like, all right, so we're gonna do this, we call it pushing hands. So basically stand in a loose, that's too far apart, in a sort of loose formation like this, and then move, we're standing forearm to forearm, and he pushes in, I go like this, block his elbow from smacking my face, roll my hand around, and then push back, and then we kind of go around and around like this until one of us makes a move to try and like push or press or get the other person off balance, whatever it is we're doing. And sometimes that's just as simple as coming over the top and like, I say hitting. Doing a gentle little tap or something like that. But oftentimes it's just kind of like getting used to where the body goes, and he was trying to show me like, okay, if I just push you like this, you should be able to just kind of move your body a little bit, and like the force of me pushing is going to get knocked off of your body. Or he's pushing here and I hit with my shoulder like this, I come up over the top and push it away from me, whatever it's going to be. So it was an interesting set of it was a little interesting the way it worked. All right, so stand from more or less bare, step out, center up, all right, go easier, go softer. He was saying I was too stiff with a lot of the stuff, which is somehow not surprising at all. That way. That way. Alright, and then the next part, I don't actually know what it is, but it does involve maybe stepping up like this and doing something else, but I don't want to get into that. So, from here, you can stand with a V formation on the feet, start with hands in bare. It is 2 in, 2 out, apparently. I was just doing it completely wrong earlier. It's alright. Don't move the... I get it. Alright, and then just for funsies, we'll do another, we'll do a karate form. Probably a black belt. What do we want? Basaidai? Oh, wow. Okay. Lost it there. Whew. Here. Fugosudo. We're here. Yeah, this is just the other one. Jump change, always fun. I can feel the Tai Chi starting to come through. Before it was very much informed by just trying to go like all out with like muscling everything, which is a bad thing to do even in karate. So typically when we're doing all of our moves in karate, typically we try to stay as loose as possible while we're doing it, and then like only snap and put a lot of effort into the movement in like the last inch or two. So that's more or less how we do things. Alright. There we go. Okay. So we're talking about the sequence limit, which is basically just going to be the, or we're going to use the continuous function in order to find the limit, which then informs that the discrete limit is going to be the same. All right. We're looking at improper integrals, So the idea here is that we do something like, if we want, for instance, from 0 to infinity of e to the negative x dx. Or if we want integral from 0 to 10 of 1 over x dx. So in these particular cases, we notice that we have a bit of a problem in that we keep having these terms which are going to not be allowed in the limits, or in the in the limits of integration. So if we're talking about going out to infinity, and then we're trying to take the integral out to infinity, there's no endpoint. So, like, how do we make that work? Right, and then same thing applies here for a rational function. If it's 1 over x and we have a 0 in that denominator, does that ever produce anything? Does that get us a valid result? So we have to now go in and say, okay, what do we get when we plug these things in? Now, you're not allowed to just plug them in. However, what we can do is we can say, hey, just like we did with the L'Hopital's rules, we can use the limit, the idea of limits, in order to be able to help inform us what these values are going to be. So here we're taking the limit as this is b goes to infinity of integral from 0 to b of e to the negative x dx. Okay, the integral of e to the negative x dx is going to be a negative e to the negative x, and it's going to be evaluated at 0 to b, where b is again having the limit applied, b goes to infinity. So the limit as b goes to infinity of negative e to the negative b minus a negative, so plus e to the 0. Right, negative 0, but whatever, it's fine. Right, e to the 0 is just 1, so that's easy enough. And then limit as b goes to infinity of negative e to the negative b, right, this is e to the negative infinity, is going to get us 0. So this is just 0 plus 1, or 1. This other one becomes a little bit more of a problem. Limit as a goes to 0 of a to 10, integral going from a to 10 of 1 over x dx. The reason I said it's more of a problem is because here, when we take the integral of 1 over x, it's going to be the limit as a goes to 0 of the natural log of x evaluated from a to 10. Which is going to be limit as a goes to 0 of natural log of 10 minus natural log of a. Okay, as a goes to 0, natural log of a is going to go to negative infinity. So it looks like the integral from 0 to 10 of 1 over x dx should be going to negative infinity. It's not particularly a nice result. It doesn't work out for us very well. So here we could say that, okay, well, this is not going to work. We're not going to get a result. It's not a finite result. So in some examples, we could have something like taking the integral from 0 to infinity of 2 over 1 plus x squared dx. Right? Improper, therefore we say this is the limit as b goes to infinity. 0 doesn't seem to be causing any problems with this. And if you know what function is the integral of the thing in the middle, the 0 isn't going to affect that either. Mostly because, you know, you could mostly tell, because even if you don't necessarily know what the function is, the 0 value here isn't going to cause any problems or like strange jumps or anything like that in this function. So probably it'll be okay when we get to the other one. Infinity is just messing us up because it's infinity. Alright, and we're going from 0 to b of, as the integral of 2 over 1 plus x squared dx. Okay, 1 over 1 plus x squared gets us the arctangent that we saw earlier. So we take the integral of that, we end up with an arctangent. The 2 is currently just a constant, so that can come out. Take the limit as b goes to infinity of 2 times the arctan of x, evaluated from 0 to b. Okay, so this is going to be 2 times the quantity arctan of b minus arctan of 0. Sorry, limit as b goes to infinity. Okay, the arctan of 0 is 0. So what angle is going to get us a tangent value of 0? It's 0 radians. And then what angle is going to get us a tangent distance of infinity? Or you could start thinking about how far do we have to go, right? What angle is going to get us a value that's... What angle are we close to as our tangent value starts approaching infinity? And that's going to be pi over 2. Now, in theory, we could also make it... no, never mind. I was thinking you can make it negative pi over 2, but that's not true, because that's going to be negative infinity. So it's specifically different. It's fine. Right, so this is going to end up being pi. Pi over 2 minus 0, just pi over 2, multiplied by 2, gets us pi. Okay. What about integral from 0 to 1 of 1 over square root 1 minus x squared dx? Okay, so here, again, we're seeing a little bit of a problem in that if we have 1 in the denominator, this is going to potentially cause a problem. We don't know necessarily if that's going to cause a problem on the other side if we take the antiderivative or the integral of this particular thing. 0 is not going to cause any problems as far as we can tell. And again, if you know ahead of time, or if you can figure out real quick what the function is going to be, whose derivative is this, then it makes it much easier, right? This should be an arc sine. Yeah. This is an arc sine derivative. So what does the arc sine look like? All right, this is going here to here, give or take. That looks terrible. Whatever, it's fine. Goes through 0, 0, has a point at either of these ends at negative pi over 2, comma negative 1, and pi over 2, comma positive 1. So it should be that we're looking at this endpoint right here. And then we're trying to find the area between 0 and pi over 2. Oh, okay. Not quite true. We're trying to find the difference between these two things. It's not quite true either, is it? No. Yeah, it's 1, which is here. That one. So we're essentially trying to find what's the height difference between these two things. What's the displacement from the 1 that I just drew up here to the 0 here. Okay, that should be what we're actually going for. So here, we're going to say, let's take the limit as b goes to 1 of the integral from 0 to b of 1 over square root 1 minus x squared dx. So then, this is going to be equivalent to the limit as b goes to 1 of the arc sine of x as we go from 0 to b. I went backwards. That's what the problem is. It's not this thing in the middle. It's the numbers. All right, this is going to be pi over 2 up here. This is going to be negative pi over 2 down here. There we go. This is going to be 1. This is going to be negative 1. And it's the displacement that we're going from here to here, which should be pi over 2 now that we're looking at it. But, you know, got to actually check. So here, taking the limit as b goes to 1 of the arc sine of b. Arc sine of 1 is going to be pi over 2. Minus arc sine of 0 is just going to be 0. So it's just pi over 2. We don't have to worry about. You know, there wasn't anything that was there that was actually improper. It's just that the 1 could potentially cause a problem because it's on the edge of the domain of... It's on the edge of the domain of the integral. So you do have to watch the antiderivative. So just watch that, make sure it's not going to end up messing it up somehow. Anything's possible, really. Okay, so what about? taking the integral from 0 to infinity of e to the negative root x over root x dx. Right, so both of these are potentially going to cause problems. Potentially. You do have a 0 in the denominator, but you may not have to worry about it. And then the infinity in the b location is going to cause a problem because we can't have infinite limits. So we take the limit as b goes to infinity, infinity. In theory, you could also make it a going to 0. It really doesn't matter. You could do that if it was just any other number as well, like 1. Perfectly acceptable. E to the negative root x over root x times dx. Now, if we want, we could say that we're going to let u be equal to negative root x, and then du is going to be equal to, take the derivative of that, it's going to be negative 1/2 x to the negative 1/2 times dx. We almost have it, right? There's a lot of stuff that's not here at the moment. That's not a lot, but we need a 2 and we need a negative in the denominator, and to balance it, then we need a negative 2 in the numerator, which is then just going to be multiplied. So we could take this negative 2 here and just bump it out. And then we say, now we've got negative 2 times the square root of x in the denominator, which is where all these things are. I guess the negative as well. And the dx. Right, we've got all the things. So now we can actually take the integral. So take the limit as a goes to 0, b goes to infinity. Again, a doesn't really matter, but yeah, it'll be fine. Negative 2 times the integral from a to b of e to the u du. It's all there. So that makes the limit as a goes to 0, b goes to infinity of negative 2 times the integral of e to the u du is just e to the u. And then here, this is going to be x is going from a to b. So now we have to evaluate x as it goes from a to b. Back substitute. We can now make u back into negative square root of x. Again, evaluated x from a to b is going to get us negative 2 times e to the negative root b minus a negative 2 times e to the negative root a. Again, here we're doing limits as a goes to 0, b goes to infinity. As b goes to infinity, this whole thing is going to go to 0 because that's going to be e to a negative infinite value, right? E to the negative x as it comes down and to the right ends up converging on 0. And then here, e to the negative root a, we get a 0, which is going to make it 2 times e to the 0, which is just 1. right, e to the negative infinity is converging on 0, not that it is equal to 0. I know some people would be very upset about it, but nonetheless. Right, so this is now going to be 2 times that 1, which is going to make us get this value of just 2. Okay, second one. Take the integral as we go from e to infinity of dx over x natural log x. Okay, so from here we have, again, limit as b goes to infinity. You could make a go to e as well, but I don't think we're going to have any problems there. Okay, interesting. Yeah, I think we're okay, but still. E to infinity. And again, here what we want to do is say we're going to do another u substitution. So let u be equal to, and let du be equal to what? Well, we have a u-du pair. If u is equal to the natural log of x, then du is equal to 1 over x dx, which we have. So then this is just going to be du over u. Easy to work with. This is x equals these. So this is the limit as b goes to infinity of the integral of du over u is the natural log of u, where x is being evaluated from e to b. We took the infinity out. It's now part of the limit. And then back substitute again, so limit as b goes to infinity of the natural log of x, not u. Evaluated as x goes from e to b. So we take the limit as b goes to infinity of natural log of b minus the natural log of e. Natural log of e is 1. Natural log of 1 is 0. Okay, and then the limit as b goes to infinity, the natural log of infinity is itself infinity. And then it's the natural log of infinity, so it's also infinity. So infinity minus 0 is just going to be infinitely large. Right, so this is a divergent. Okay, and then have the integral from 0 to 3 of x over x squared minus 1 raised to the 2/3 power dx. So I don't know immediately what the problem is. It could be the 0 is most likely what the issue is, but like, it doesn't look like there's a problem immediately. So we could just say, let A be 0, B be 3, and then worry about that at the end. Okay, so in this case, we can let u be equal to x squared minus 1, and du be equal to 2x dx. Hey Stuki, how's it going? Welcome back. Right, so let's just suggest for the moment that we're going to take the limit as a goes to 0, b goes to 3, and then we'll sort out what the problem is after we take the integral. Cracking the GRE Math Subject Test. Second edition, 2002. Yep, I figured, why not, right? I know a couple of people on YouTube have thanked me for posting these, so I just wish that, like, I potentially could have gotten it out before they took their exam. Not as much free time, yeah. Alright, so we did not have entirely everything that du was going to be, but, you know, we did alright. So, du also needed a 2 here to make it 2x dx. Let's just do that, and then we balance it by putting a half either on the outside or just on the inside, and then we move it out. So, equivalent. It's all good. So, integral from a to b, and again, let's figure out what the problem is with the integral limits of integration after. Okay, so now we've got 2x dx is going to be du over, this is going to be u raised to the 2/3 power. Now, from here, we could also say, okay, look, in order to get a negative 2/3 power, this would have had to have come from u to the 1/3. Like we did this earlier with the cube root one. So that 1/3 would have dropped down as a power. So we would need an additional 3 in the denominator, which means we need an additional 3 in the numerator to balance that out, which will allow us to just do antiderivatives rather than like working through, oh no, what extra term do I need here? Anybody can still do this, and they would just say, okay, well, I'm going to do du over u to the 2/3, so the constant that we would have needed was 1 over the new power, which is 1/3. So 1 over 1/3 just gets us a 3 on the outside again. Just like that one over there. I'm pointing that way. Just like that one over there. So we do a limit as a goes to 0, b goes to 3 of 3/2. This is going to give us a u to the 1/3 evaluated, x is evaluated from a to b. And then back substitute, limit a goes to 0, b goes to 3. 3/2. U is x squared minus 1 raised to the 1/3 power going from a to b. X equals, not that we need it anymore because now all our variables are the same. And I'm not seeing a problem for either of these numbers. So we could just plug in the limits as they are. We don't need to leave them improper. So 3/2 times, this is now going to be b is 3 squared minus 1 raised to the 1/3 power minus 3 halves times 0 squared minus 1 to the 1/3 power. Or I guess we could have left it as 3 halves times the quantity and then just done that difference of those two terms. It's all good. This is going to be 3 halves times. This is going to be 9 minus 1 is 8. And 8 to the 1/3 power is going to be 2. Okay, minus 3 halves times 0 squared is 0, minus 1 is negative 1. Take the cube root of negative 1, we also get negative 1. And then that gets multiplied by negative 3 halves to make positive 3 halves. So 3 halves plus, this is 2 divided by 2 is just 3. So 3 plus 3 halves is going to get us 9 halves. 4.5, whatever you want to do with that. Just to make sure. Yes. Since both of these integrals converge, we can conclude that the original improper fraction converges, and therefore this all works. Yeah. So what did they do? Oh, okay. I get it. Alright, so the issue was this thing. X squared minus 1 raised to the 2/3 power creates a cusp. That was the issue. Right, x over parentheses raised to the 2/3 x squared minus 1. Oh, it's even worse than a cusp. Okay, so that is actually infinite. So it may be useful to graph these ahead of time just to take a peek at it and figure out what the issue is. So yeah, going from 1 to 3 means that we're going to go from this asymptote to 3 here. Evaluate the integral of that stuff. Right. You got to clock just what's going on in each of these individual functions. So, yeah. So I did say that when we were doing this with like some of these other ones, the issue wasn't necessarily apparent. So, like for A, right? Having a 0 in the denominator would be a problem. So if we do e to the negative square root x all over square root x, right? This was going from 0 to infinity, and so the 0 is going up to an asymptote that way, and infinity is going out to a horizontal asymptote, but again, it's an infinite limit, which is what the problem is. So yeah, because our 0 is going off to infinity, we should check the original function to see what it is looking like, and then are there any problems based on that. So here e doesn't make any issues with this particular function. It's going to be e times natural log of e is 1. So 1 over e. Right, this is 1 over x natural log x. Oh, nope. Oh, no. 2.7. Right. Right. E is 2.718. Close enough. We're here, right? This is the start of this particular function. If it was 1, if we were going from 1 to infinity, then that would cause problems, and we would need to double check what's going on with that. All right, cool. And come to think of it, right? If we did this as 1 to infinity, that, right. If we did it as a 1 in the initial space, that would end up getting us natural log of 1 is 0, and natural log of 0 is negative infinity. In theory, this is still negative infinity, or negative infinity, so positive infinity. It would be infinity plus infinity, so it'd at least be determinate. It would be infinite in extent. But that would still be a problem because it's a divergent integral. Alrighty, cool. How long have we been going? Almost 2 hours. Stuka, do you have any, like, favorite improper integrals? Excuse me one sec there. Sorry to put you on the spot. And I suppose something that would be acceptable for a Calculus 2 level. Secant of x dx from 0 to pi over 2. Okay. Secant squared, yeah. Although does secant squared make it go to infinity? I mean, it certainly goes to infinity faster. Does it make it go to infinity entirely? That'd be tangent. Right, so here, secant squared of x dx is going to go off pi over 2. This is 1 over cosine squared, so their cosine value at pi over 2 is going to be 0, therefore secant value is going to be infinite. And then we go from 0 with a value of 1, head off toward infinity. We say, like, okay, what's the limit as b goes to pi over 2 of 0 to b of secant squared x dx. It's again going to be a tangent of x going from 0 to b, where the limit b is limited. B is going to pi over 2 from the negative side. That's also important. That'll work. Limit b goes to pi over 2 from the negative side of the tangent of b minus tangent of 0, because we don't need to worry so much about that. Then this is going to cause this to, this is just 0, and then the tangent of b is going to be infinite in extent, so this is going to be divergent. Yeah, we probably should not get into the next section, which is all about infinite series, because that's going to be like an entire day. Always fun. Yes, that is definitely just its own topic, its own can of worms, because woof. My spouse has written all over the unit review in this section. This is back in the day when we took it. Well, anyway. I think it's probably a good stopping point, honestly. So we'll snooze this. And, let's see. Tomorrow and or Friday we may do some Elite Dangerous. I may also break out 9 Souls again and try to finish the game, because I'm like this close to getting it. I had Igong down to like a quarter health at 1 or 2 of the runs, and it was just maddeningly close, and then she broke out some new thing that I've never seen before. I'm like, come on. But I did notice that my reaction time to all the rest of the stuff is proper. So it's like right on. I'm like, yeah, that's good. Okay. Let's go see who is on. Penn Center's on for math. Okay, good. So yeah, let's go see Penn. Nini? What'd I do? If anybody is interested, we do have the Ko-fi link up there. You can subscribe as always, but never required. We don't really do anything during the breaks, so you know, nobody's missing out on anything except just having ad-free viewing. At some point, we might end up putting up a channel trailer or like best clips or something like that if we ever get decent clips. And if you want to seek out clips, feel free to, you know, watch some of the VODs, and if you see something funny or mathematically important, go ahead and pop that in. So, gonna head over and see Penn Center. Like I said, we'll be back tomorrow and or Friday for 9 Souls and or Elite Dangerous. We have a big Distant Worlds 3 event which is coming up to explore a very remote part of the galaxy where the people who are running the event have also created like little events to have a little bit of fun with. So we'll see you all then. Hope you all have a good night. My name's Obi-Wan Pez. This is N Simplex Pachinko. We'll catch you next time. Thanks for coming.